Welcome everyone. I'm Rati Ludhani, pursuing PhD at Department of Mathematics, IIT Bombay. I'm a PMRF fellow here. Today we'll discuss sample questions related to week 5. So let's begin. So consider the permutation group H6. So you're familiar with permutation group, right?
Yes, ma'am.
Okay. So you just consider S6 and you can write all the elements. Is that okay? So all the elements in the form of cycles. So have you taken any course on group theory?
No, ma'am, but I know symmetric group and partition. Six means 11 partition. We can write one cycle types.
Yeah, exactly. Yeah, so you can have either one. So basically, these are all the bijective maps from 1 to 6 and 1 to. So, for example, I'll just write S4 for. Uh, so S4 is basically 1, 2, 3, 4. So you need to write all the bijections you have. So either you can just map everything to itself. So it's like 1 goes to 1, 2 goes to 2. So you can actually write it just identity. And second element you can take 1 goes to, for example, 1, then you can take 2 goes to 2, 3 goes to 4, and 4 goes to 3. So as a cycle form, 3 goes to 4 and you are done, and 4 goes to 3. So like that you can get 1 2 1 3 1. So actually these are also 24. I should go little small, so I'll just write S3. So for S3 you will have just identity. You will have 1 2 2 3 and 1 3, and then you will get 1 2 3 1 3 2. These 6 elements will be there. So what will be the cardinality of S6? So if you know that.
9 factorial.
6 factorial, exactly. So basically how this is coming, you have all the bijective maps. So you will go up to 1 to n, and for 1 there are n possibilities. So you have n possibilities with so to map 2 to anything, you have n minus 1 possibilities, because 1 is mapped to something, so that element will be removed because you need bijective maps. So 2 can map to n minus 1 elements, so there are n minus 1 possibilities. 3 will map to not those two elements, so you have n minus 2 possibilities, and so on. And n will have just one possibility to map, so you have n factorial elements. So in Sn you will have n factorial elements. Okay, so yeah, as in the first part. So first says cardinality. So cardinality of S6, we can write it in this form. Sorry, S6, or in general Sn, is n factorial. So in particular, cardinality of S6 is equal to 6 factorial. Okay. Okay, let's see the second part. What is the order of element 1 2 3 4 5? So what is the order? Order says order of any element sigma. Sigma is a, why we write it sigma? Sigma is a bijective map. Okay, so order of any element sigma will be what? Minimum of k, such that sigma raised to power k is equal to the identity. So identity, either you write it this, or maybe I'll write I. Okay, uh, or maybe one more thing. So k belongs to p. So just the positive non so okay, yeah, so we are just taking positive integers, not 0. Okay, so 0 will be identity that we are not considering. So positive integers. So minimum of these k, will just take it. So that will always exist. That is a theorem in the notes that you can check. So let's see what will be the order of sigma. So you have 1 2 3 4 5. So you need to do square, cube, because you know that this is not identity for sure, because 1 is not mapping to 1. So that is one option. So you can check square. So square is square you will get. So when you do square, so do you know how to multiply these? So I'm not writing comma, is that okay? I hope there will be no confusion. Is that okay? Mahalakshmi?
Yes, ma'am. Yes, ma'am.
Okay, okay. Yeah, so I'm not writing comma, is that okay? I hope this is clear. So what we are trying to do, we are trying to find the order, the order of the element 1 2 3 4 5. So basically there's a LCM theorem, but you can actually see that when you take, when you, so basically I'm trying to find a square. So when we do a square, so how to do the multiplication, where one map to 2, and when you, so this is always right to left. So one map to 2, and now where 2 maps to 1. So 1 maps to 1 itself. So this is just a cycle. Is that clear?
Yes, ma'am.
Okay, it is not showing again. I'll present again. Yeah, it is showing now. Yeah, so 1 maps to 1 itself. Now where 2 maps? 2 maps, now you have 2. 2 maps to 1. So here 2 maps to 1 and 1 maps to 2. So you will get 2 only, right? So 2 maps to 2 itself. Okay? Is that okay? Now where 3 will map? So you start with 3. So can you tell me where 3 will map?
4.
So in this cycle it will map to 4. Now where 4 maps? So you are coming from right to left. So 4 will map to 5.
Yes,
So
ma'am.
this is composition. So you can see this in the bijective map itself. You are just doing f of g. So basically you are doing f of f, because these are same cycles. So the multiplication is like where 3 maps, so 3 maps to 4, and now in this multiplication there is a 4 appearance of in the left part also. So 4 will map to 5, so 3 will actually map to 5, and it will not close at this place. Now where 5 will map, 5 is mapping to 3, and where 3 is mapping, 3 is mapping to 4. So it will map to 4. And now where 4 will map, so 4 is mapping to 5, and now 5 is mapping to 3. So 4 is mapping to 3. So cycle is closed. So this multiplication is like that. Is that clear?
Yes, ma'am.
Okay. So similarly, if you do cube, then you will get so 1 2 will stay like this, and you will get identity. So you will just get 3 4 and 5. And when you do 4, so you will get actually so this will be just identity. You can check that. You'll get 3 4 5, and next at 3 4 5.
You are writing.
Oh, okay, again. Yeah. Okay, this is part of the lecture now. Presenting again and again. That's okay. Yeah. So similarly, when you do 1 2 3 4 5 raised to power 5, you will get 1 2. Here you will get 3 5 4. And when you do 6, then actually you will get identity for everything. So that is the least number you will get. So actually, there's a theorem on it for any, no, like sigma 2, these are the cycles, for example.
Then the LCM of that
Yeah,
cycle.
exactly. LCM of cycles. So you just take, for example, you have sigma 1, sigma 2 up to and so on, sigma r. Then this k, then order of this sigma will be LCM of the cycle type, LCM of all the lengths of cycle. So in this case you have 1 2 and 3 4 5. So the order of sigma will be what? LCM of this cycle has length 2. Okay, again. Okay, why this is happening? And there's one option I can do. Yeah. So uh, LCM of 2 and 3, right? So you'll get 6. So you know that, right? Okay. So what about the third part? Can 5 be the order of any element of S6? Can 5 be the order of any element of S6?
1 5, ma'am.
Sorry?
The partition 1 5 get order 5 now.
Yeah,
Cycle.
so Cartesian you mean, so this na?
Yeah, partition 1.
Hmm.
One is a identity cycle and 2, 3, 4, 5.
Yeah.
Yes.
Yeah,
Yes.
you can do this. Yeah, anything like you just fix one, and from the rest of the numbers you just take a cycle. So exactly that will have the order 5. And yeah, there's a well known theorem in group theory, that any element, the order of any element will divide cardinality of the group. So basically S6 factorial. So sigma, the order of the element has to divide 6 factorial. So for example, if I ask, can 7 be, for example, if I change it to 7, can 7 be the order of any element of S6? No, because this does not satisfy this property, because 7 does not divide 6 factorial.
Yes, ma'am.
Okay, so this is something general. So you can always check if it is a divisor of cardinality of the group. So that is S6. So this is in general true for a group, not just permutation group. Okay.
Yes,
Okay,
ma'am.
let's move to the next one. What is the inverse of this element? 1 2 3 4 5. Okay, so you have this 1 comma 2 3 4 5. So what will be the inverse of this element? So let's say this is the sigma. So basically what we are doing, you have 1 2 3 4 5. Inverse is basically, okay, I'll just write once. So 1 is going to 2 and 2 is going to 1. 3 is going to 4, 4 is going to 5, and 5 is going to 3. See, this is happening. Now inverse is what? You just invert it. So what does that mean? When you compose it, 1 2 3 4 5, I'll just do this. Okay, so composing, so inverse is what you just take, this is sigma, and if you take sigma inverse, then you should get identity. Identity means everything mapping to itself. So you have 1 2 3 4 5. When will it happen? You are mapping 1 to 2, now again you map 2 to 1. Okay, then only it will happen. You just invert it. 1 is mapping to 2, then 2 is mapping to 1. Then when you compose it, sigma inverse of sigma, then 1 will map to 1 itself, because 1 is mapping to 2. Now you want it to be 1. So what you are doing, you are just inverting it. Now 1 was mapping to 2, now 2 should map to 1. Okay, when you compose it, you will get identity only. 1 will map to 1. Similarly, 1 is mapping to 2. 2 is mapping to 1. Now you want 2 to map to 2 only. So 2 is mapping to 1, and again you just take 1 is mapping to 2. Okay, so this is something. So what you're doing, you're just inverting. 1 is mapping to 2, then take in inverse, just take 2 should map to 1. So what it will be, so 1 2 3 4 5, 1 2 3 4 5. So sigma inverse, what you want it. So sorry, I'll just write it here, sigma inverse. So 1 should map to where? Yeah, 1. So here 1 is mapping to 2, so you want 1 is mapping to 2, so 2 should map to 1. Okay, so I'm just trying to clear it. So 1 is mapping to 2, 2 is mapping to 1, 3 is mapping to 4, 4 is mapping to 5, 5 is mapping to 3. Actually 1 is mapping to 2, you take 2 should map to 1, which you have taken. 2 is mapping to 1, so you should take 1 is mapping to 2, so that is okay. So this is not something which is making any difference. Now in the second part you check it. So 3 is mapping to 4, 3 is mapping to 3 is mapping to 4, so you should take 4 should map to 3. So 4 is mapping to 3. Okay, now so 3 is mapping to 4, so you have inverted it, so 4 should map to 3. Now 4 is mapping to 5, so 5 should map to 4. So 5 should map to 4. And now 5 is mapping to 3, so 3 should map to 5. So this is the inverse. So you just invert it, because you know that when you compose it, you will get identity. That is the requirement. So in the cycle, what you should do, sigma is 1 2 3 4 5. So what you can do, you can just write it in the other order. So other order means you just write 2 1, and you write 4 5 5 4 3. Okay,
Yes, ma'am.
okay, you just write it from the other side. You just, and these are disjoint cycles, so there will be no issue. So you should have always disjoint cycles, so always write it in the form of disjoint cycles, which is there. And just for inverting, you just write it in like other way around. You just write from right to left, don't change the order. So 5 4 3. Now you know that in your answers you could have, for example, these are cycles. So this is same as 3 5 4, right? This is same as 4 3 5, right? You know that. So this is same as this is a cycle. So cycle could start from anything. It's like a necklace.
Yes, ma'am.
Okay, so this is same as these two options. So whenever you are checking the options, these are same, so you can check it like this also. Okay, so for inverse, you just write it from the other side. So 5 4 3 will be. Okay, so this is the inverse. Okay, now what is the cycle type of 1 2 3 4 5? So cycle type is, can you tell me cycle type of this?
2 and 3.
Yeah, 2 and 3 exactly. You just need to write the length.
Mm.
So cycle type. So cycle type, oh okay, one more thing, cycle type you should write it in this form, 3 comma 2. So we always take monotonically decreasing sequence. So you just take the bigger number first and then the lower number later. Okay, So this is a way to write it. So cycle type of is of this kind. Okay. How many elements are there in S6 of cycle type 3, 2, 1? So how many elements are there in S6? So of cycle type 3, 2, 1. Okay, let's check. You have cycle type 3 to one more thing. This is something I did wrong. So cycle type is always with full cycle. So 6 is not here. So 6 means 6 is mapping to identity, right? So the sum should be 6, sum should be n. So this sum, whatever you are writing, 3, 2, 1, sum should be 1. That means you need to write identity ones also, like which are mapping to itself. So cycle type is like this. Okay? So for example, if you have 1, 2, or the identity map, or everything is mapping to itself. So the cycle type will be 1 comma 1 comma 1 comma 1 comma 1. So these are 6. So the sum should be full. Sum should be 6. Okay?
Mm.
Yeah. Okay. Next.
Partition, ma'am.
Sorry?
Partition, number of partition.
Yeah, the partitions exactly. So yeah, number of part and the partition of n exactly. Cycle type is actually defining partitions of n. Very good. So 3 to yeah, so you have given the cycle type to be 3 to 1. Now you need to find out how many elements are there. How many elements are there with this cycle type? So that means, so one example, you can have 1, 2, 3, 4, 5, and 6, right? So you, oh, okay, again.
Uh,
Yeah, it is visible now. Yeah.
uh,
So yeah, how many elements are there with this cycle type? Yeah, I did that. So 1, 2, 3, 4, 5, and so this is one option because it has cycle type 3, 2, 1. So you
yes.
need this cycle type. Okay, don't be confused with the cycle. So that's why I'm not writing commas here. Okay. So yeah. So cycle type says one cycle of length 3, one cycle of length 2, one cycle of length 1, which is there. Okay, so you need to find out all the elements. So how will you find it out? You need to count such kind of such elements. So you cannot write all the elements like this. So what you can do, you can just do combinatorics thing. So you just count it in a way. So out of these six, out of six elements, you so basically what I'm doing, so you have 3 cycle, you have 2 cycle, and you have 1 cycle. Okay, so you have this. So you have 3 options, you have 2 options, you have 1 option. Okay, so you need to count it. Yeah, you need to count. So for this one, so for first cycle, what you have 6 options. Out of these 6, you at first place you can have 6 elements. For the second one you can have 5. For the third element you can have 4 options, right? Okay, now after this you have used 3 elements. Now you have just 3 elements left as an option. Now you have 2 elements as an option. Okay, yeah, and then you have 1 option. So basically 6 factorial options are there for all the basically these are all the permutations. But what are the things which are making it particular? So you have these many options. Now you know that if you have a cycle of this kind, a1, a2, a3, so you have this. Now this is same as a3, a1, a2, right? This is same as a so you have so you can start with a2. Now a2, a3, a1. So these are all, these 3 cycles are same, right? Okay. Yeah, yeah,
Again.
yeah. Yeah. Just a second. So basically I'm saying for the first cycle, Yes. Yeah, so what I was saying, if you have A1, A2, A3 as in the first cycle, if you have A1, A2, A3, then this is same as A3, A1, A2, and this is also same as A2, A3, A1. So this is like a necklace. So cycles are same. So these are in the same equivalence class. So these cycles are same. That means you have to divide by 3. So in the first part, these are counted 3 times. Okay, right?
Yes, ma'am.
Similarly with these two, so you can have either 1 2, and this is same as 2 1. So you have to divide by 2. And similarly, yeah, similarly, okay, this is not showing again. I'll try the other thing. Yeah, it is visible now. So yeah, 3 into 2 into, now you can have, for the last one you can just have 1. So basically you need to divide by r. Okay, so whichever the cycle length, you have to divide by that. Okay, one second, I'll try. So is that clear? This will be the cardinality of all the cycles which has cycle type to be this 3 2 1. Okay, one second. I'm trying one thing, so I hope this will be. Just a second. Yeah. So yeah, this will be your cycle. Yeah, number of cycles, number of permutations with cycle type 3 2 1. Okay, is that okay?
Yes, ma'am.
So this is how you can actually calculate. Okay, now let's. So this was the last part. Yeah, let's move to the next question then. Find the number of 4 2 necklaces with 2 beads of one color and 2 beads of other color. Okay, so you have this like uh, cycle form 1 2 3 4. It's like your necklace. So you have 4 places, and you are allowed to color with 2 colors, maybe red or white, whatever you want to choose. So for example, you can color this to be white, this to be red, this to be white, this to be red. So they are asking find the number of 4 2 necklaces. 4 2 means 4 are the n is equal to 4, and the number of colors are 2. So with 2 beads of one color and 2 beads of other color. Okay, so this is one option. You can have anything else. So this you need to calculate. I should write using Polya's enumeration theorem or formula. Okay, you need to calculate using that. So what does that formula says? Formula says, if you remember, cardinality of G. So yeah, so basically you have been asked this. So this is when you take 1 to 4, this is like a cycle, because you have been asked in a necklace. So necklace is a cycle. So in a cycle it's like 1 2 3 4. So you can consider the permutation group of 4. You can take a subset, and G to be equal to the set generated by the cycle 1 2 3 4. Okay, this is the cycle 1 2 3 4. Okay, and you can have, so what are all the elements you will have if it is generated by 1 2 3 4? You take this square will be what? 1 will go to 3, so you can actually check, and 2 will go to 4, and the sigma cube, which will be the inverse, it will be 1 4 3 2, or you can actually write as we just did 4 3 2 1. That will be the inverse, and you will have identity.
Ma'am, 1324, how it comes, ma'am?
1 3 2 4. So this is the square. So if you take sigma, this is sigma square, this is sigma cube, and this is sigma raised to power 4. So it's when you take this square, it's like 1 2 3 4 and 1 2 3 4. So where 1 will go? So you write 1 will go to 2 here, and 2 is going to 3. So 1 will go to 3. So you are taking the composition. Just go right to left. Now where 3 is mapping? 3 is mapping to 4, and 4 is mapping to 1. So 3 is mapping to 1. So this will be closed. Now you start with next number, which is 2. So 2 is mapping to 3, and 3 is mapping to 4. So this will be 4. And now where 4 is mapping? 4 is mapping to 1, and 1 is mapping to 2. So 4 is mapping to 2. So it will be closed. So this is how you calculate it. So you can do it with the maps. This is exactly from the maps itself, composition of maps. Is that okay? Yeah. So this is your G. So from Polia's enumeration theorem, it says you take this 1 mod G and you take summation. So if we can check the lecture notes if you want. So this says, yeah, Polia's enumeration. Yeah, this one. So how will you do? So this says you calculate this part. So you calculate this part 1 by cardinality of G and this. So this is what? Summation sigma belongs to G, and you take, what is the notation? Yeah, P mu. So P mu sigma. So mu sigma is the cycle type, and yeah, you write. So you have just two colors. So this is basically the you will go up to x1 to xk, and you have just two colors. You will stop here. So this is the way that you can also check using the example. That will help you. So you need to find the coefficient of x1 square and x2 square. So because you are saying two beads should be colored with two beads should be colored with one color, two beads should be colored with the other color. So this is what you need. You need the coefficient of this element. So now let's check. Cardinality of G is 4. Now you take P mu sigma x1 x2. So what is this? This is actually so this is, again, if you want to check, this is, yeah, here. So how will you do that? P mu x1 to x mu is, you take the multiplication mu I. So if this is the cycle type, then you will have P mu I, and mu I is what? X1 raised to power, those powers you will take. Okay, this is the way. So here what you will, so for one example, so mu sigma is what? So first one, so mu sigma is 1 2 sorry, this is cycle type 4. So you have just 4. Okay, x1 cycle type is just 4 because you have one length of cycle 4. Sorry, cycle length is 4, or one cycle is of length 4. Okay, plus you will get the second one is this. So you have two cycles of length 2. So 2 comma 2, that will be x1 comma x2. Next you will have P4321. So you again have a cycle of type 4. So you just multiply by 2 in the first one. And identity is 1 1 1 1, because you have 4 cycles of length 1. So you'll get x1 comma x2. So you need to calculate this. Now let's calculate. This is 1 by 4. Now what is this? This from the formula, this is like x1 raised to power 4, x2 raised to power 4. This is exactly what I am doing from this one. So I am using this. So you have P22 is equal to x1 square plus x2 square. Okay, and then x1 square plus x2 square again, because you just take all the cycle lengths like for this, and then for the last one you will have x1 plus x2 plus x3 plus x4. So sorry, what I mean to say, you will write x1 raised to power the cycle length of first one, that is 1, x2 raised to power cycle length of first one again. So you will take for each cycle length, you will write it this, and there are 4 of these, so you will take the power. Just see the thing, you will if this is fast you can actually check it. So for each cycle length, this one, for mu1 you will write mu1 for everything, and then for mu2 you will write second bracket with x1 raised to power mu2 up to and so on xk raised to power mu2, like this. So you'll get this. So here you need to find coefficient of x1 raised to power 2 and x2 raised to power 2, because which represent you have so this is 2 beads of one color, 2 beads. So 1 2 here, this suffix 1 2 represents suffix 1 2 represents colors. Okay, so 2 beads, so power represent how many? So 2 beads of one color, and second says this one, 2 beads of other color. Okay, so we need to find the coefficient of this. Let's see from which it will come. So this part will not give x1 square x2 square. Here you can get it. So you have x1 square, you multiply by x1 square can be multiplied to x2 square, and x2 square can be multiplied to x1 square. So you will have this one. So from this part you will get this much, plus from this second part what will you get? So this is x1 plus x2 whole raised to power 4. So let's see what is this. So x1 square plus x2 square plus 2x1 x2. I'm just expanding squares first. So square into square. Okay. So x1 square can be multiplied to x. So we just need the coefficient of this one. Okay, x1 square into x2 square. And from this part you will get this multiplication. Okay, so you will get 2 times, and then from this part if you multiply these two, so you'll get 2 into 2 4 x1 square x2 square, so plus 4 x1 square x2 square, and there are some symmetric terms or something, but I'll just write terms. Okay, so here you get 6 x1 square x2 square plus some terms. So here 6x1 square x2 square. So in total you have 8x1 square. From first one you get this, from second you get this. Okay, so this one, and it is divided by 1 by 4. So you divide by 1 by 4, so you will get 2x1 square x2 square. So coefficient of x1 square x2 square is 2. So that will exactly, from the Polya's enumeration theorem, that will tell you there are two. So answer is 2. So there are two necklaces with two beads of one color and two beads of other color. Is that okay? So you just need to find coefficient of corresponding symmetric term, not term, monomial. Okay?
Okay, ma'am.
Yeah, you can try that. So this is the way to calculate. Okay, let's move to the other question. Okay, this is not, yeah. Find the number of automorphisms of the graph. So you have this graph. You need to find number of automorphisms. Now, what is the meaning of automorphism of a graph? So automorphism, so sigma is an automorphism of a graph if, or maybe I'll write this is with so of a graph, basically we write it like v comma e, so vertices comma edges, if if so basically when you take sigma, so you are taking vertices to a different place. So if yeah, if v1 sorry vi is connected to vj by an edge, then so this is not a directed graph, so that could be anywhere. Okay, so this is not directed, so two elements could be connected, that is the main point. So there could be an edge from, for example, from v1 to v2. Now what does this say? If there is an edge, there should be an edge between their sigmas, like between their images also. So that is if this, if and only if. Okay, you can write like this. So basically what it is saying, if there is an edge between the two elements, then there should be an edge between their maps also, between their images also. Is that clear, the definition?
Yes, ma'am.
So let's see what do we have here. Can we do something in this question? So you have you have this figure. Now there's a very good way to count that. You just count the degrees. So basically you know that if there is there will be an edge when it has, for example, at this point there are two edges going out. Okay, so degree of, so there's a term degree of v1 is 2. So you just count how many edges are going out of it. Okay, so degree of v1 is 2, degree of v2 is, can you tell me how what is the degree of v2?
3.
3, exactly. Degree of v3 is
3.
3, degree of v4
2.
yeah, and degree of v5 is
4.
4. So firstly, you know that what is degree? Degree is saying how many edges are there to connect with that point, with that vertex. Okay, now so what I want to say, if it is mapping to somewhere, then it should have the same degree. So sigma of v1, degree of sigma of v1 should be same as degree of v1, because you want edges to be the same, like you want a edge between those two elements, right? So if the degrees are different, degree of v1 and degree of sigma v1 is different, then you will have the lesser number of so if in the map the degree is lesser than the degree of v1, then the edges will be less. So that is not allowed, because you need the count same count, and with this condition, so degree should be the same. Yeah,
Automorphism means function defined from itself.
yeah, there's a bijection. So if so yeah, there's a bijection between yeah, automorphism means the sets are same. Isomorphism is usually used for different sets. So yeah, automorphism is used when you have the same sets and you want a bijection. So there's a bijection, and now this bijection has some property. You cannot just map v1 to v2 or v3 to v5, anything. You cannot do like this. You have to satisfy this condition. If there is a edge between two vertices, then there should be an edge between the maps of those vertices, like between the images of those vertices. Okay, so the key point is the degree of the so basically we are saying degree of vi, sorry, yeah, degree of vi should be same as degree of, sorry, degree of vi should be same as degree of sigma vi. So the image should have the same degree. So let's see how many possibilities are there for this. So firstly, 4 is there, okay, and 4 is nowhere. So v5 has to map to v5 for balancing degree. Is that clear? So
Yes,
v5 has to, so there is one automorphism always, identity. Okay, so you have identity automorphism. Now you are checking is there any other automorphism or not. Okay, so v5 is mapping to v5. Now v1, where v1 can map. So identity we have already taken. So let's map v1 to somewhere else. So we can always map v1 to v1, but let's check if there is any other possibility. So v1 is mapping to 2. Sorry, degree of v1 is 2. So it cannot map to 3, 3. So there is one possibility of v4. Okay, so it can map to v4. Okay, now what about v2? So there are two possibilities for v2. So we have already taken one option of, like, we are going different from identity right now. So v1 is mapping to v4. Let's fix that. Now where v2 can map, v2 can either map to okay, one more thing. So if v1 has been mapped to v4, then v4 has to map to v1 because there are just two elements of degree 2.
yes, ma'am.
Okay, so this is the combined package. And now what about v2? So v2 can either map to v2, there is one possibility, but it could also map. So there are two possibilities. I'll write, there is one possibility with this condition. So cases, sub cases. A second is v2 can map to v3 because the degrees are same. And whenever v2 will map to v2, then v3 has to map to v3 because that is the only possibility left, because 3 is already mapped. And when v2 will map to v3, then v3 has to map to v2. Okay?
Yes,
Yeah.
ma'am.
So these are two possibilities. Now let's check if both of these are possible or not. Let's check about this one. So you have v5 mapping to v5. So I'll write it like v1, v2, v3, v4 and v5. You have v1, v2, v3, v4 and v5. So v1 is mapping to v4, v4 is mapping to v1, v5 is mapping to v5, v2 is mapping to v2, v3 is mapping to v2. Now we need now let's check the edge part. Okay, so we are saying v2 is mapping to v2. So for example, see, v1 and v2 has an edge, right? There's an edge between v1 and v2. So their images should have an edge between those, right? So sigma of v1, we have sigma of v1, we have chosen it to be v4, and sigma of v2 we have fixed it in the first case. So now we have to check whether there is an edge between v4 and v2. Is there any edge between v2 and v4?
No, ma'am.
No. So this is not possible. So this discards this possibility. Okay, so now this one is left. Actually you can check that this is okay, this works. Now because what is happening, if v1 is mapping to v4 and then v2 is mapping to v3 also, so there's an edge, so there will be no issue. Okay,
Yes, ma'am.
so this will work. So there are two automorphisms. One is identity, One is identity, other one is this one, v5 mapping to v5, v1 and v4 has alternate things, and v2 and v4 has to have alternate things also. So you can actually calculate like this and have all the options. Okay, so you just need the count to automorphism. Let's move to the next one. Find the number of automorphisms of the graph this v3, v2, v1, v4. Again the same thing we will do. Let's count the degrees. One second. Yeah, let's count the degrees. So degree of v1 is
3.
3. Degree of v2 is
1.
1. Degree of v3
1.
1. Degree of v4 1. Right? So
Yes.
now you can see that there is fixed possibility for v1. v1 has to map to itself. Okay, so if you take any sigma is automorphism of this graph VE, let's write. So automorphism of this graph, then sigma, first option, sigma is identity, so that is there always. Okay, and the other one is like sigma of v1 has to be v1. Okay, or maybe I'll not write identity, I'll write it in general. So sigma of v1 is just v1. There's one possibility, whatever sigma you choose, you have to map v1 to v1. Now what about v2, v3 and v4? If you see, there is a symmetry in this case. So actually if you observe, sigma of v2 has all the possibilities. Either it could map to v2, either it could map to v3, either it could map to v4.
Yes, ma'am.
Okay, because there's a symmetry. If you see, because it is just connected with v1, so if there is an edge between v1 and v3, there's an edge between v1 and v2 also, so you can map v2 and v3 definitely. Similarly, if there's an edge between v1 and v3, there's an edge between v1 and v4. So there's if you map v3 to v4, you will have your symmetry, and there is just one edge between these elements. Okay, yeah. So basically v2 can map to 3 elements. There are 3 possibilities. Now if v2 has been mapped to these three elements, then v3 has 2 elements option, right? If for example v2 is mapped to v3, then v3 can only map to v2 or v4, and again v4 has one option. Maybe I'll write options. So again you can use permutation thing. So you have 3 options into 2 options into 1 option. You need to find the cardinality. Okay, and so basically you are counting where so v1 has one option, then v2 has 3 option, v3 has 2 option, v4 has 1 option. So basically you have cardinality to be this 3 into 2 6 automorphisms are there. Is that clear?
Yes, ma'am.
Okay, so this was the last question of mine, so you may tell me if you have any doubt.